Hello everyone, welcome to week 5 of Intro to Analysis. In this lecture, we're going to talk about the monotone convergence theorem, subsequences, and the Bolzano-Weierstrass theorem. Okay, so let's talk about what monotone increasing and monotone decreasing mean. So a sequence is monotone increasing if a sub little n is less than or equal to a sub n plus 1 for all n. So if the previous term is smaller than or equal to the next term for all n. Likewise, a sequence is called monotone decreasing if a sub little n is bigger than or equal to a sub n plus 1. So the term before is going to be larger than or equal to the next term for all n. And if a sequence is either monotone increasing or monotone decreasing, it is simply monotone. So let's look at some examples here. The sequence n is monotone increasing because we have 1, n equals 1, n equals 2, n equals 3. And so you can see that a sub n is going to be less than or equal to a sub n plus 1. So the previous term is always going to be smaller than or equal to the next term. 1 over n is monotone decreasing. Starting at n equals 1, we have 1. N equals 2, we have 1/2, 1/3, and so forth. And so we can see that the previous term, a sub little n, is always going to be bigger than or equal to the next term, a sub little n plus 1. Okay, and so just a sequence of ones is both monotone increasing and decreasing. If we just have 1, 1, 1, 1, 1, 1, etc., we can see that a sub little n is going to be bigger than or equal to a sub little n plus 1, in particular equal, and likewise a sub little n is less than or equal to a sub n plus 1, in particular equal. Okay, so equality works here for these monotone definitions. Okay, so our first big theorem of this lecture is going to be the monotone convergence theorem. And we're going to prove one part of it, and then the rest is going to be an exercise for homework. And so let's just state it first. So if we have a monotone sequence, whether that be monotone increasing or decreasing, then the sequence is going to converge if and only if it is bounded. Okay? So if a sub little n is increasing, then if your sequence is unbounded, it's going to diverge to infinity. And if your sequence is bounded, it's going to converge to the supremum of the set of the terms in your sequence. Okay? And similarly, if your sequence is monotone decreasing, then your sequence, if it's unbounded, it's going to diverge to negative infinity. But if it's bounded, it's going to converge to the infimum of the terms, of the set of terms in your sequence. So let's, maybe I should have put this a few slides ago, but, let's just look at a few examples of what this looks like pictorially. Okay, so we have monotone increasing and bounded. The monotone convergence theorem says if it's monotone and bounded, it's certainly going to converge. And by this picture, you can see that this dashed line appears to be the limit. So this is going to converge. Okay, so if we look to the right, monotone increasing and unbounded, there's no limit that this thing is approaching. And so it looks like our sequence here is going to be a sub n is equal to 2 to the n. Just based on, I think that's, okay, so a sub n equals 2 to the n. That's going to diverge. When n gets larger, so does a sub n. So this is an example of a monotone increasing and unbounded function. So this is going to diverge to infinity. All right. So here on the left, we have monotone decreasing and bounded. And so just from the looks of the sequence, we can see that it looks like it's getting closer and closer to 0, or the x-axis. And so that would be our proposed limit here. Okay, so this is monotone decreasing and bounded, so this converges. And then to the right, we have an example of a monotone decreasing and unbounded function. And so we can see here that as n gets larger and larger, this thing is decreasing without bound. So this diverges to negative infinity. And I didn't put it here, but this diverges to infinity. Okay, so some examples of the monotone convergence theorem pictorially. Let's look at some examples of some sequences that are not monotone. Okay, so we can't use the monotone convergence theorem to deduce anything about where the sequences converge, if they converge, because we don't have the monotonicity. And so you can see that this guy is not monotone. Remember, for monotone, we either need that the previous term is smaller than or equal to the next term, or the previous term is always going to be bigger than or equal to the next term. Okay, and so this guy was monotone increasing, this guy was monotone decreasing. And we can see here that this guy appears to be decreasing, right? We're going from the previous term to the next term. But then it starts, if we look at the term after that, it starts increasing again. And so that's not monotone. We want a picture that either goes like that, continuously downward, or it goes continuously upward like this. Okay, and so likewise here, this guy is not monotone. It does appear that this sequence is going to converge, though, which is fine, right? But it's not monotone. Okay, because, you know, we have these things jumping around. We don't have a pattern of going continuously up or continuously down. And similarly here, it looks like this sequence is going to converge, but it's not monotone because we have things increasing, then we have the next term decreasing, then increasing, then decreasing. But we want this, okay? We want every single term to either the previous one to be smaller than or equal to the next one, or the previous one to be bigger than or equal to the next one. Okay, so that's monotone. Okay, so let's do a proof of the monotone convergence theorem. And we are just going to do the increasing case. We'll do the case where our sequence is increasing. And I'm going to denote increasing with this up arrow pretty frequently and decreasing with the down arrow. Okay, so your homework, I think, is asking you to prove the decreasing case. It'll be very similar to increasing case. Okay, so we have two things to work with, or we have two cases that we need to work with. The first one is if our sequence is increasing and unbounded, and the second one is if our sequence is increasing and bounded. And so remember what we're trying to show. We're trying to show the following. Okay, the first thing we're trying to show is that if our sequence is monotone increasing and unbounded, this means that our sequence is going to diverge to infinity. So that's the first thing we want to show. And the second thing we want to show is that if our sequence is monotone increasing and bounded, then our sequence is going to converge. And in particular, it's going to converge to the supremum of the set of terms in our sequence. So we need to show these two things. So first, let's show one. So here's our proof. Okay, so we're going to suppose that a sub n is unbounded. And what does that mean? Okay, well, we know that a sub n, let's actually write it here. A sub n is increasing, monotone increasing, and unbounded. Okay. So since we're increasing, this means that for this thing to be unbounded, then for any positive m bigger than 0, there exists a capital N such that some term in our sequence, a sub capital N, is going to be bigger than m. Okay, so that's what it means for this thing to be unbounded when we're increasing. So for any positive number, there's going to be some term in the sequence that's bigger than that positive number, no matter how big you make the positive number. Okay? So we have the following. We have, for little n bigger than n, this implies, well, remember this thing is increasing, so the previous term is always going to be the previous term is always going to be smaller than the next term since it's increasing, smaller than or equal to. So if we have little n is farther, so we're thinking about things farther along in the sequence, little n bigger than capital N, then it follows that a sub little n is bigger than or equal to a sub n, and by this assumption we have a sub capital N is bigger than m, and this is because our sequence is increasing. That's why we have n bigger than capital N implies that a sub little n is bigger than or equal to a sub capital N. So this guy is further along in the sequence than this guy, and since it's increasing, the little guy is bigger than or equal to the capital one. Okay? And so what does this imply? Well, this implies that a sub little n is bigger than m. And so by definition 3.4 in the lectures, this means that our sequence goes off to infinity. This is definition 3.4. Okay, so just using the definition of being unbounded and increasing, and the definition of what it means to diverge to infinity. Okay, so let's do the next case. So now we show 2. Okay, so what are we supposing here? So we're going to suppose, again, that a sub n is monotone increasing, and that a sub n is bounded above. Okay, so since our sequence is bounded above, all of the terms in our sequence are bounded, and so And so the set of all terms in our sequence is bounded, and so it has a least upper bound by completeness. Okay, so let's write that out. So we claim that our sequence converges to the supremum of the set of terms in our sequence. And we'll call this set A. Okay. So because our sequence is bounded, this set A is going to be bounded. So since A is bounded above by completeness of the reals, A has a least upper bound, aka supremum. Okay, and let's call the supremum alpha. Okay, so let's do some scratch theorem, or some scratch work. I'm gonna do this in orange to just show that this isn't part of the official proof. And so what do we want? We want to show that that our sequence A sub n converges to alpha, okay? So we want A sub n converging to alpha. And what does that mean? Well, that means by our definition of convergence of sequences, we have that for each epsilon bigger than 0, there's a capital N in the naturals such that little n bigger than capital N implies that the terms in the sequence get arbitrarily close to alpha. So the difference of A sub n and alpha is going to be less than epsilon. Okay, so this is what we want. So I'm just going to keep this up here to show that that's what we're trying to get to. Trying to get to this conclusion here. All right, so here's the continuation of the proof. All right, by the supremum analytic theorem, and in the notes I listed that, it's different in the textbook, but in the notes I listed it as theorem 1.3. So what did this say? This said that for every epsilon, there was something in the set. So in our case, the set A is this, the set of terms in our sequence. Okay, so by the supremum analytic theorem, for each epsilon bigger than 0, there is something in the set. So some A sub capital M, N. There's some A sub capital N in the set for which A sub capital N is bigger than alpha minus epsilon. Okay, so that was the supremum analytic theorem. Okay. All right. So in order to get this conclusion, we want to first suppose that little n is bigger than capital N. So let's do that here and see what comes out. So suppose little n is bigger than capital N. So because the sequence is increasing, monotone increasing, because little n is bigger than capital N, that means that A sub little n is further along in the sequence than A sub capital N, right? And so we have the following. We have that by this guy, we have A sub capital N is bigger than alpha minus epsilon. But since capital N is not as far along in the sequence as A sub little n, and since the sequence is monotone increasing, that means that we have A sub capital N is smaller than A sub little n. And I'll put this in parentheses since our sequence is monotone increasing. Okay, so we have this guy because of this guy. Oops. Sorry about that. All right. Okay, and remember that we're trying to arrive at this conclusion. Okay, so let's ditch the A sub capital N and just write things in terms of A sub little n. So, what do we have? Well, we want to bound A sub little n by things with alpha and epsilon, right? Because we can use our inequality properties to get something that looks like this at the end if we work from that start. So so what do we have? Well, we know from this inequality above that A sub little n certainly bigger than alpha minus epsilon. We also know that alpha was the supremum of the set. And what does it mean to be the supremum? Alpha being the supremum means that it's going to be bigger than or equal to anything in the set, any A sub little n. So that means that this guy is going to be less than or equal to alpha. So let's go ahead and write that down. So we have A sub little n is going to be less than or equal to alpha for all n. And that is just because alpha is the supremum of the set A. Okay? So remember that epsilon is just a positive number, any number bigger than 0. And so if A sub n is less than or equal to alpha, then A sub n is certainly going to be less than or equal to alpha plus epsilon, a little bit more, right? And so we just have A sub little n is going to be less than alpha plus a bit more, right? We're trying to get it symmetrical on both sides of the inequality so that we can use those inequality properties to bring in our absolute value up here. Okay? Okay, so this is going to be bigger than alpha minus epsilon. And actually, we can make this strictly smaller since epsilon was a positive number. Okay, so now if I want to get epsilon on both sides, I subtract epsilon from everybody, right? This is kind of what I was going for. This A sub n, I'm sorry, not minus epsilon, minus alpha. Oh, the coffee hasn't kicked in yet. So I'm trying to get that, right? And so if I subtract epsilon from everybody, alpha, not epsilon, sorry guys, I get that A sub n minus alpha is going to be less than epsilon and bigger than negative epsilon. And what does this mean? Well, I think it was our very first or second lecture of the course, if we have this situation, this means that we have the absolute value of A sub n minus alpha is less than epsilon. And somewhere I should have put let epsilon be bigger than 0. Let's see. Yeah. So maybe I should have put it up here. So by supremum analytic, for every epsilon, there's some... Okay. So maybe I should put it up here. Let epsilon be bigger than 0. And so we arrive at our conclusion here. Okay, so that's the proof of the monotone convergence theorem increasing, and as I said in the homework, you'll do the decreasing case. Okay, so let's put this theorem into action. This is a pretty cool problem that I found in your book. So let's say that we have a sequence a sub n, where a sub 1 is 0.1, a sub 2 is 0.12, and so forth. We're just, like, on the nth term, we're adding the digit n. And so, like, a sub 12 is going to be all of this. We're just adding on 12 to the previous digits, okay? All right, and so we want to prove that this thing converges, and we can use the monotone convergence theorem to do so. And I'm going to abbreviate monotone convergence theorem with MCT pretty often. So MCT will allow us to do this. Now, we're not going to figure out what this converges to, but we can at least say that it converges. So, first of all, we can see that a sub n is always going to be less than or equal to a sub n plus 1. So the previous term is always going to be smaller than or equal to the next term, right? Because we're adding on digits onto this decimal. Okay, so that's pretty clear, I think. So monotone increasing. Okay, and so the next part we need for to use the monotone convergence theorem is boundedness. Okay, and we can see that, you know, this thing, since it's always going to start with 1, okay, it's never going to start with a 9, right? If we had 0.999999999, that thing, we might have a problem there, but since we have a decimal expansion in this form, what we can say is that for each n, for each little n, a sub little n is going to be less than or equal to 1. Okay, so this thing is never going to be 1 no matter how many digits we add, because we can see that the first digit is 1 and it's not 9 or anything. You know, this thing isn't getting even remotely close to 1. So we can say that each term is going to be bounded above by 1. So the sequence is bounded above by 1. Then, by the monotone convergence theorem, a sub n converges. All we needed was that it was monotone and bounded, and we get convergence by the monotone convergence theorem. So we know it converges, and yeah, I like this example. It's pretty cool. Let's take a look at this one. So we have a recursive sequence here, which means the next term of the sequence is defined using the previous term. So we have a sub 1 is equal to 1, and we have the next term, a sub n plus 1, is equal to a n plus 1. And the idea here with these recursive sequences is that it's easy to show that they converge by using the monotone convergence theorem. It's not so easy to show that they converge using just the definition of convergence because of the recursive defined structure here. I mean, it's possible, but it's easier to work with the monotone convergence theorem. So let's get a feel for what's happening here to try to, because remember, to use the monotone convergence theorem, we need two things. To use MCT, we need, first of all, that the sequence is monotone, increasing or decreasing. And the second thing is that the sequence is bounded. So we need both of these things. And so let's get a feel for what's happening here so that we can prove that both of these things are true. Okay, so a sub 1 is equal to 1. A sub 2, which is a sub 1 plus 1, is just going to be a third times the previous term, which was 1. So 1/3 times 1 plus 1, that's going to give us 2/3. Okay, so a sub 3 is going to be 5/9. I'm just going to do this so that we can kind of see what's happening here. A sub 5 is 41/81, and so forth. Okay, and so if we look at what's happening to the terms in our sequence, it appears that the sequence is monotone decreasing. Appears monotone decreasing. Right, because the previous term is larger than the next term in each case. So that is the first thing. And then the second thing that what looks like what looks to be the case for our boundedness is it looks like this stuff is bounded below by 1/2, right? Because we're going from 5/9 to 14/27, which is a little bit bigger than a half, and then 41/81, which is still a little bit bigger than a half, and so forth. And so it looks like this is bounded below by a half. So let's justify these two things so that we can use the monotone convergence theorem. Okay. All right. So the first claim is going to be we're going to justify that this thing is indeed monotone. So a sub n is monotone decreasing. And what do we need to show for that? So we need to show that the next term is always going to be less than or equal to the previous term for all n. Okay, that's what it means to be monotone decreasing. So I think the easiest thing to do here is an inductive argument. So remember, this is what we're trying to show right here. And remember, for induction, we need to show the base case, so the smallest little n that holds. And then from there, we'll use the inductive hypothesis to prove the general case. Okay, so for the base case, we want to say, so the smallest possible little n in the naturals is 1, right? And so for the base case, is it true that a sub 1 plus 1, which is a sub 2, is less than or equal to a sub 1? So is that true? Well, a sub 1 is 1, and a sub 2 is 2/3, so yeah, that's true. So 2/3 is indeed less than or equal to 1, and so the base case is shown. All right, so for our inductive hypothesis, right, so for our inductive hypothesis, we're going to assume that a sub n plus 1 is less than or equal to a sub n for all n bigger than or equal to 1. And then we're going to show that the domino effect happens, that a sub n plus 2 is less than or equal to a sub n plus 1 with this assumption. Okay? So what is a sub n plus 2? A sub n plus 2, just by definition of the recursive sequence, it's going to be 1/3 times a sub n plus 1 plus 1. Okay, so our inductive hypothesis says that we can assume that this is true. And because of this, because a sub little n plus 1 is less than or equal to a sub n is less than or equal to a sub n, then this whole thing is less than or equal to 1/3 times a sub n plus 1. We're just using this in green to get to this line right here. Okay, and this is exactly equal to a sub n plus 1 by the definition of our recursive sequence. Okay, and so what we've shown is a sub little n plus 2 is indeed less than or equal to a sub n plus 1. Okay, so, and we're done. So by induction, it follows that our sequence is monotone decreasing. Okay, so the next thing to check is the boundedness condition. We have 1 now. And the next thing to check is that our sequence is actually bounded, and just from our scratch work off to the side, we think that this thing is bounded below by a half. So let's check that. And maybe I'll do that starting over here. Okay, so now we claim a sub n is bounded below by 1/2. And what does that mean mathematically? That means that a sub little n is bigger than or equal to a half for all n in the natural numbers. And again, we can show this by induction. So by induction, so maybe I'll just write it. So we can show this by induction. So the base case, we want to show that this is true for the smallest possible little n. And the smallest possible little n is little n equals 1. That's the first natural number. So is it true that a sub little 1 is bigger than or equal to 1/2? Well, yeah, that's true, because a sub little 1 was 1. 1 is bigger than or equal to 1/2. So that's true. So the base case is done. Now assume the inductive hypothesis. Okay, so assume inductive hypothesis. So we're going to assume that a sub little n is bigger than or equal to 1/2 for all n bigger than or equal to 1. And then we want to show that this is true for the next guy in line, which is a sub n plus 1. So a sub n plus 1, by the definition of our recursive sequence, is a third times a sub little n plus 1. Okay, and by our inductive hypothesis, this guy is going to be bigger than or equal to a third times 1/2 plus 1. Just using the fact that a sub little n is bigger than or equal to 1/2, I can substitute it in like that to get this inequality. Okay, so then this equals 1/2, and therefore a sub n plus 1 is bigger than or equal to 1/2. Alright, so we've shown that we have this domino effect by induction. So, for any little n, a sub little n is going to be bigger than or equal to 1/2. So that means that a sub n is bounded below by 1/2. Okay, so by the monotone convergence theorem, this thing is going to converge, and it's going to converge to some limit. So I'm going to write this over here. So we've shown 1, the sequence is monotone, and 2, the sequence is bounded. And so by the monotone convergence theorem, the sequence is going to converge to some limit L. We don't know what it is yet, but you probably have an idea from our scratch work. Okay, so we're going to, because I told you that it's difficult to work directly with the definition of convergence with these recursively defined sequences, we're just going to use the definition of the limit from calculus to justify this claim. And so, remember, maybe I'll write it up here. We have a sub n plus 1 is going to be equal to, well, how did we define it? A third times a sub n plus 1. A third times a sub n plus 1. So this is what we were given, and we're claiming that a sub n converges to L. So note, this is an important concept to understand, that the limit as n goes to infinity of a sub little n, okay, so we're saying that this does have a limit, okay, it exists, and it's some capital L. So note that this is going to be exactly equal to the limit as n goes to infinity of a sub little n plus 1, right? Because since we're going to infinity, these two things are equal, right? We're making n as large as we want, and so the limit of these guys are going to be the same. Maybe you've seen this justified in another class, I'm not sure, but this is the key idea here. And so maybe I'll write it up here actually, that that the limit, in parentheses, the limit as n goes to infinity of a sub n is equal to L. Okay, I'm just going to write that in parentheses. That's what that means, to converge to L. Alright, so we're going to use this and take the limit of both sides. So we're going to take the limit as n goes to infinity of a sub little n plus 1 And that's going to equal the limit as n goes to infinity of a third times a sub little n plus 1. Okay, and so we said that this thing equaled L, right? And so that means that when I'm taking the limit of a sub little n plus 1, that's also equal to L. So we have L is equal to, right, just using this side, limit as n goes to infinity of a third a sub little n. Now, limit as n goes to infinity of, well, actually, let me go ahead and, let's go ahead and, like, simplify this first. So, limit as n goes to infinity of a third a sub n plus a third. And so when we take the limit of a third, you know, if we take the limit of this, it's going to give us a third L by the algebraic limit theorems. And when we take the limit of this as n goes to infinity, well, there's no n to deal with, so it's just the same, 1/3. And so what we end up getting is L equals a third L, just using the fact that the limit as n goes to infinity of a sub n is equal to L, plus a third. And so when we solve for L here, we get our limit is equal to 1/2. So indeed, by monotone convergence theorem, we know that the sequence converges to a limit, and we have deduced here, by the way that our sequence is defined recursively, that that limit has to be 1/2. Okay, so let's take a look at our next proposition that I'm calling proposition 3.1. So suppose we have a set in the real numbers that's bounded above. Then there always exists some sequence where each term in the sequence is in our set, and that when we take the limit as n goes to infinity of a sub n, we get the supremum of the set. And we have an analogous definition for the infimum. So we're going to go ahead and prove the supremum case, and you should try and prove the infimum case on your own. But let's go ahead and do this. So what are we trying to show? Okay, so we'll show the following. When S is contained in R, let's say if the set is bounded above, then there exists a sequence a sub n where each term in the sequence is in the set, and the limit as n goes to infinity of a sub n is going to be the supremum of the set. Alright, so let's go ahead and prove this. Alright, so we're going to suppose the hypothesis. Suppose that we have a set in the reals that's bounded above. Then, by completeness, it has a supremum. It has a supremum. Let's call it alpha. Call it alpha. Okay, let me make sure I'm recording. Okay, we're good there. All right, so what do you think we're going to use here? Well, we have a supremum, so it probably makes sense to look at the supremum analytic theorem. By theorem 1.3, supremum analytic, for each epsilon given, there is some little a in our set such that little a is larger than alpha minus epsilon. Okay, so you give me an epsilon, I find you a little a in my set that has this property. And we can use this to kind of make a sequence. So, you know, for epsilon equals 1, we can say that there's some little a1 in our set, right, that's bigger than alpha minus 1, right? When you give me epsilon equals 1, I find you a little a1 in my set by the supremum analytic theorem. Similarly, if I give you epsilon equals 1 over 2, then we have that there's a little a, there's a a2 in our set S that's bigger than alpha minus 1/2. And I think you can see where this is going. I give you epsilon equals 1/3. There's an a3 in our set that's bigger than alpha minus 1/3. And in general, you give me an epsilon equals 1 over n. There's an a sub little n in our set bigger than alpha minus 1 over n. And we're claiming that this guy, this sequence, is going to converge to alpha. Okay, that our a sub n is going to converge to alpha. Okay, and so one thing to note is that a sub n is not equal to alpha minus 1 over n. It's just saying, okay, a sub n is greater than alpha minus 1 over n. It's not our actual sequence. But we can name this sequence right over here something. Let's call it, let's see what I called it in my notes. Let's call it Cn. So let Cn be equal to alpha minus 1 over n. So the idea here is to use the squeeze theorem for sequences, right? We're trying to deduce that this guy converges to alpha, and we know just from like looking at this by inspection that this sequence Cn is going to converge to alpha. When I make n really large, this thing's going to go to alpha minus 0, which is alpha. And so I want to bound a sub n in between two sequences that converge to alpha. And so this is going to be one of them because I know that a sub n is going to be bigger for each n. It's going to be bigger than alpha minus 1 over n. So that's kind of the intuition here. And we're going to let the other sequence be alpha, right? Because we know, you know, maybe I'll write this off to the side here as scratch. We know that a sub n, just from this work up here, is going to be bigger than alpha minus 1 over n. And we know that since alpha is the supremum of our set, we know that for each little n, this is going to be less than or equal to alpha. And so the idea here is to use the squeeze theorem. Okay? All right. So we have the following. We have that a sub n is going to be bigger than alpha minus 1 over n. And then alpha, taking the limit, I should have put this guy right here, less than or equal to. Okay, well, alpha is just a constant, so it doesn't depend on n, and so this is just alpha, right? This goes to alpha. This goes to alpha because we know that as n gets really large, 1 over n goes to 0. So by the squeeze theorem, since we've sandwiched this sequence in between two other sequences that converge to the same limit, we know that limit of the guy in the middle is going to be the same thing as the guys on the outside. And we're done. Okay, so that was the proof of that proposition 3.1. Okay, and we can see this in practice here with just a small example. So we have a bounded set in the real, so 3, 4 is acting like our capital S. And we can find a sequence, so that proposition tells us that we're guaranteed to find a sequence A sub n that converges to the supremum of the set, which is 4. And we're also guaranteed to find a sequence that converges to the infimum of the set, which is 3. And each term in our sequence is going to be in the set 3, 4. Okay, so what's a solution to this? We could say A sub n is equal to 4 minus 1 over n plus 1. We can see that making n really large is going to have this converge to 4. And we could say that our other sequence B sub n that's converging to the infimum is 3 plus 1 over n plus 1. We can see that as n gets large, this thing's going to 0, and so this whole thing's going to 3. And it's easy to show the following. So it's easy to show that for each n, A sub n is actually in the set, and B sub n is actually in the set. And I'll just illustrate this quickly with A sub n. And you can convince yourself that this is true for B sub n. So for A sub n, since little n is a natural number, it's going to be bigger than or equal to 1. Okay, so I'm looking at this top piece right here. And if I'm trying to get this expression, and so what I can do to get closer to that is to add 1 to n. And so if I add 1 to both sides, n plus 1 is bigger than or equal to 2. And so just do the algebra. 1 over n plus 1 is less than or equal to 1/2. Multiply by a negative to flip the sign. And then I'm going to add 4 because I'm trying to make it look like that. So if I add 4 to both sides, 4 minus 1 over n plus 1 is bigger than or equal to 4 minus 1/2, which tells us that 4 minus 1 over n plus 1 is bigger than or equal to 3.5. And it's going to be less than 4. So also okay, because suppose not, then 4 minus 1 over n plus 1 will be greater than or equal to 4, and we end up with a contradiction. If we subtract 4, we get negative 1 over n plus 1, bigger than or equal to 0. We can multiply by n plus 1 since it's positive always, and we end up getting negative 1 is bigger than or equal to 0, which is a contradiction. And so 4 minus 1 over n plus 1 is less than 4. It's greater than or equal to 3.5, but less than 4, so it's in the set 3, 4. And you can do the same thing for B sub n. Okay, so the next definition I want to talk about is the definition of the word subsequence. Okay, so if you have a sequence, a sub n, of real numbers, we're going to let n1 be less than or be strictly less than n2, less than n3, and so forth. And so this is just an increasing sequence of natural numbers. So n1 is just a number. It could be 5, it could be 6, it could be 7, whatever. Then a sub n1, a sub n2, a sub n3, and so forth is called a subsequence of the sequence a sub n. Okay, so, and we're going to denote it a sub nk, where k is in the natural numbers, and this indexes the subsequence. So a sub n5 is the 5th term in the subsequence. A sub n8 is the 8th term in the subsequence, etc. So let's look at some intuition for this, because I know that this definition is a little weird. Let's see. Okay, so if I just take a regular sequence, a sub n equals n, what does this look like? This is 1, 2, 3, 4, 5, 6, 7, and so forth, okay? So a subsequence is going to be, we're going to start somewhere in the sequence with an n1. We don't know where. Well, I mean, you can start anywhere you want in the sequence. What if I wanted to just illustrate like plucking out the even numbers as a subsequence? So if I wanted 2, 4, 6, 8, 10, 12, what if I wanted that to be my subsequence? Well, then I could consider the subsequence a sub 2n. Okay, and so that's just going to be 2, 4, 6, 8, 10, blah, blah, blah. And so this guy is going to be the first term in our subsequence. This is a sub n1. Okay, this is going to be a sub n2, a sub n3, a sub n4, and so forth. Okay, and so and so we can see that this guy is going to be the second term in my original sequence, right? This guy is going to be the 4th term in my original sequence, a sub n2, and so forth and so forth. Okay, so that's the idea here. We don't have to have like a specific rule for defining a subsequence. All that matters is that your n1 is less than n2, less than n3, etc., etc. And so here, like if we look at this guy, we have n1 equals 2 because it's the second term in our original sequence. N2 equals 4 because it's the 4th term in our original sequence. And so forth. So n3 equals 6. Yeah, and so forth. But we don't need a rule. We could have something like this. So we could have the subsequence, let's say a sub nk. We could define it like this. We could say it's maybe 1, 2, 5, 106, 153, 2011, I don't know. Whatever. So there's no pattern, but that's a perfectly valid subsequence because we have this guy, this n1 is 1 because it's the the first term in our original sequence, a sub n equals n. This is the second term, so n2 equals 2. N3 is going to equal 5. Right, because this is the fifth term in our original sequence. N4 is equal to 106, and we see that N1 is less than N2, less than N3, less than N4, so it's a perfectly valid subsequence. We're just plucking out numbers from the original sequence, and we're not changing the order. Like, we're not going 1, 2, 3, 2, 1. Like, you know, it's we're going up. We're in the sequence. Yeah, and so if you wanted to list the terms in the subsequence, you would say a sub n1 is 1. So the first term in our subsequence is 1. A sub n2 is 2. A sub n3 is 5. And so forth. A sub n4 is 106. And there's no rule, but that's totally fine. All right, so let's look at some more examples of subsequences. So let's say my original sequence is 1 over n, and let's say that my subsequence is 1 over nk. Okay. And so maybe our subsequence is defined by 1, 1 over 3, 1 over 5, 1 over 7. And so n1 is going to be 1, n2 is going to be 3. That's the third term in our original sequence, 1 over n, and so forth. N3 is going to be 5, N4 is going to be 7, and so forth, okay? And so in our subsequence, a sub n1, the first term in our subsequence is 1, the second term in our subsequence is 1/3, and so forth and so forth. Okay, so we're just plucking out terms in our original sequence. Okay, what about this one? So our original sequence is still 1 over n, and so our subsequence is defined by this list of numbers, 1/10, 1 over 100, 1 over 1,000, and so forth. And so what's our n1? This is going to be the 10th term in my original sequence, so n1 is going to be 10. n2 is going to be 100. It's going to be my 100th term in the sequence 1 over n, and so forth and so forth. So if I list out the actual terms in my sequence, a sub n1 in my subsequence is 1 over 10, so it's the first term in my subsequence. A sub n2, but it's the 10th term in my original sequence. A sub n2 is 1 over 100, so forth and so forth. Okay. All right, and as I mentioned before, we don't have to have a well-defined pattern like we did in the last two examples. We could have something that looks like this, and this is a totally fine subsequence because the NKs are strictly increasing. We're going from 2 to 25 to 16, 129 to 100, that whatever. So it's, you know, perfectly valid subsequence. 2, 25, 16, 129. Yeah, and I'm really like going through this carefully because I remember this confused me when I was first learning this stuff. So, first term in our subsequence is 1/2. Second term in our subsequence is 1 over 25. And again, we have this correspondence between, so this guy is the 25th term in my original sequence, 1 over n, right? But it's the second term in our subsequence. Okay. Just want to make that clear, that correspondence. Yeah, and so forth. So a sub n3 Okay, so those are subsequences. Let's give some non-examples of a subsequence of 1 over n. To talk about subsequences, we need an original sequence, so I'm using 1 over n in this example. And this guy is not a subsequence because we have n1 is equal to 10, but n2 is equal to 5. And that's a problem because we need n1 to be strictly less than n2. So this is not a subsequence. Similarly, we have repeats, right? We need strict inequality. We have n1 is equal to n2, which is 1. And we can't have this. We have to have n1 is strictly less than n2. Okay, so the next big theorem we have is that if we have a sequence converging to a limit, then every subsequence of that sequence also converges to a limit, and vice versa. If we have every subsequence of a sequence converging to a limit, then the original sequence converges to that limit. So we're going to prove this, and I'm only going to show the forward direction. So we're going to assume that a sequence converges to a limit, and we're going to show that every subsequence also converges to that limit. And then we'll leave the backwards direction as an exercise. Okay, so for this forward direction, we're supposing that our original sequence converges to a limit L. And so we're going to suppose that AN converges to L. And what does that mean formally? That means that this means for all epsilon bigger than 0, there exists some capital N such that whenever little n is bigger than capital N, so whenever you go off far enough in your sequence, the distance between a sub n and L is going to be smaller than epsilon. Okay, so this is our assumption, and we're trying to show that every subsequence of a sub n also converges to little l. Okay, so we're going to let an arbitrary subsequence of a sub n be a sub nk. So we're going to let this be a subsequence of a sub n. And what do we want to show? We want to show that this converges to the same limit L. So if we go far enough in our subsequence, so if, once little k is large enough, once we go out far enough in our subsequence, the guys in our subsequence are going to get arbitrarily close to our limit L. Okay, so what does this mean? All right, so what do we want to show? So we want to show, I'm just going to write what I just said, that for all epsilon bigger than 0, there exists some capital N1, okay, so some capital N1 so that when k exceeds N1, so when you get to a certain point in your sequence, the terms in your sequence, your subsequence, get closer and closer to L. Such that little k bigger than n1, so we go out far enough in our subsequence. This implies that the terms in our subsequence are getting arbitrarily close to L. Okay, so this is what we're trying to show. And so the first thing that we want to note, that for all k, we have n sub k is going to be bigger than or equal to k, right? And so to see this, let's just draw a little picture to help us understand what this means. So let's say that we have our sequence is 1 over n. And so this is going to be, so when n equals 1, we have 1, n equals 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, dot, 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 dot. And so we, by this assertion right here, we should have that the term in our subsequence, a sub n1, should be bigger than or equal to a sub 1. A sub n2 should be greater than or equal to the second term in our sequence, and so forth. And this makes sense, right? I mean, we could take our subsequence to be our original sequence, and we could say that the first term in our subsequence is 1, the second term is 2, the third term is 3, and so forth, right? So we see that n sub 1 is at least 1 in this case, right? This is a sub 1, a sub 2 is 1/2, a sub 3, so n1 equals 1, n2 equals 2, whatever. But we can also push our subsequence further along the sequence, so we could have something like this. So again, our original sequence. Now this is all scratch work, so I'm gonna just box it in orange so that we just kind of ignore it with our proof. But anyway, so here's our sequence again. We could make our subsequence start further along. We could say that this is a sub n1, this is a sub, well, maybe we can even do this. We can do a sub n2 is right here, a sub n3 is right here, and so forth. And so this time, n1 is equal to the third term in our original sequence, so n1 is equal to 3. N2 is equal to 5 because it's the fifth term in our original sequence, and so forth. So n3 is equal to 7, and we can see that in general nk is bigger than or equal to k. So n1 is bigger than or equal to 1, blah, blah, blah. Okay, so we can, push our subsequence farther along like that. So this is going to be an important observation in the proof. Okay, so I'm going to go ahead and just keep writing down here. So we have that nk is bigger than or equal to k. And we kind of, had the intuition there. And so so again, we're trying to find a capital N1 so that when we go far enough in our sequence, when k is bigger than capital N1, we get that the terms in our subsequence get arbitrarily close to our limit L. Okay, and so now we know we have something bounded by k. We have nk is bigger than or equal to k. And so at this point, what we can do is we can say, we can choose capital N1 to be equal to n. So if we go out, remember the subsequence is, it's a subset of our original sequence. Like the terms are going to be a subset of our original sequence in the same order that our sequence is going. So if our sequence is decreasing, our subsequence is also going to be decreasing. And so what this is saying, it's saying, we know that the original sequence, we can pick an arbitrary, we can pick a capital N for every epsilon and ensure that our original sequence is within epsilon of our limit L after this capital N. And so similarly, we can apply the same logic with our subsequence. So if we choose N1 to be equal to capital N, then what falls out is the following. Remember our hypothesis, what we're trying to show. So we want to show that this guy, little k bigger than N1, implies this guy. Okay? So So let epsilon be bigger than 0. And what do these two things imply, right? Well, we have n sub k is bigger than or equal to k, and k bigger than n1. I should have written that up there first, but this implies that we have this is bigger than n1, and so we have little nk is bigger than n1, and since capital N1 was equal to capital N, this implies that nk is bigger than capital N. So now we're far enough in the sequence for convergence to happen by our original hypothesis, that if you're far enough in your sequence, so if your subscript is bigger than capital N, then this holds true, right? And so in this case, we have nk is bigger than capital N, so the distance between a sub nk and L is going to be less than epsilon. And that's the forward direction. All right, so by the convergence of, remember, if we're far enough in the sequence, that means that that all of the terms in the sequence after that point get close to L. Okay, and we're done with the forward direction, and I'll just leave the backwards direction as an exercise. Okay, so let's go ahead and do some examples where we figure out the limit of the original sequence by using subsequences. Okay, so suppose we have b in between 0 and 1, and we want to prove that the sequence b sub n converges, and we want to find its limit. Okay, so the first thing that we're going to note is that for all b in this neighborhood between 0 and 1, we have that b is bigger than b squared, bigger than b cubed, and so forth. And all of these are going to be bigger than 0 when b is between 0 and 1. And so just to see this, for example, if b is equal to a half, we have that this holds true. We have a half is bigger than a fourth, bigger than an eighth, and so forth. And all bigger than 0. Okay, so this is the first thing that we're going to note here. And we note that the sequence for a chosen b is going to be, by this note, it's going to be decreasing, and it's going to be bounded below by 0. By the above note. Okay, so what does this mean? Well, we can use the monotone convergence theorem, right? We have boundedness and we have monotone decreasing. So the monotone convergence theorem applies, and this means that this sequence is going to converge to some limit L. Thus, by MCT, b sub n is going to converge to some limit L. We're not sure what it is yet, but we can figure this out by using subsequences. Okay, so consider the subsequence. Consider the subsequence of bn, b to the n. Consider the subsequence. Oh, great. My pen just ran out of juice. I'm going to charge it and come back on. Okay, so pen is charged. Let's continue on. Okay, so we're going to consider the following subsequence of the sequence b to the n. So the subsequence is going to be b to the 2n. And so, if we fixed b equals 1/2, then the first term in our subsequence would be b squared, which is going to be 1/4. The second one is going to be the fourth term, which would be 1/16, and so forth. Okay. So the point, what's the point? All right, the point is that we know that our original sequence converges to L. We're not sure exactly what L is, but we can use the fact that the subsequences are all going to converge to the same limit as well. So remember, by our previous theorem, we have that a sequence converges to a limit L if and only if every subsequence also converges to L. So, since b to the n converges to L, we know that its subsequence b to the 2n also converges to L. So we know by the previous theorem that the sequence b to the 2n also converges to L. Okay, and so now we can do some sorcery and figure out what this limit is. We know that b to the 2n is equal to b to the n times b to the n just by exponents, right? And so if we take the limit as n goes to infinity, both sides, okay, and so this goes to L, right? And each of these guys go to L as well, so we have L equals L squared. And so this means that L is either going to equal 0, right, if we have L squared minus L equals 0. Yeah, factoring out an L, we have L equals 0 or L equals 1. But remember, we have a monotone decreasing sequence, and it's bounded below by 0, so it's going to converge to the infimum, and that's certainly not 1, right? It's going to be 0. And therefore, our sequence converges to 0. Okay, so that's some little, some sorcery that we can use the subsequence converging to the same limit to figure out what our limit actually is. Okay, so here's a corollary to our previous theorem, and that is if you have a sequence who has a pair of subsequents converging to different limits, then the original sequence diverges. And we can see this with our classic example, a sub n equals negative 1 to the n. So if we write out the terms in our original sequence, so we have, for n equals 1, we have negative 1. For n equals 2, we have 1, and so forth. It oscillates between negative 1 and 1. And so we can consider two different subsequences. What about the even terms? Okay, so the even terms, we have the a sub 2n, so this is a subsequence. A sub 2n is going to be the second term in our original sequence, so it's 1. And then we have the fourth term when n equals 2, we also have 1, 1, 1. Okay, so this converges to 1. So this is a subsequence subsequence converging to 1. Okay, and so this is going to be a sub n1, a sub n2, a sub n3, and here we have n1 equals 2, n2 equals 4, n3 equals 6, etc. So subsequence converging to 1. We also have a sub 2n plus 1. So these are going to pick out the odd terms in our sequence, or the odd term starting at 3. And this is going to give us -1, -1, -1, etc., etc. So this guy is our a sub n1, and so we have n1. Well, that's gonna be the third term in our sequence. Okay, so when n is equal to 1, we get that this is a sub 3. So this is going to be our third term in our sequence, our original sequence. This is a sub n2. This is the fifth term. So n2 equals 5, etc., etc. Okay, so this is a subsequence converging to -1. Okay, and so by this corollary, I cannot say this word, corollary. By this corollary, since the original sequence has two different subsequences converging to two different limits, then the original sequence diverges. Okay, and so we can have something like this where there's no, there's not like a listed rule for what the sequence is, but we can kind of see from the pattern that this thing has a subsequence converging to 1/5 and another subsequence converging to -1/5. So this means that the whole sequence diverges. Okay, so our next theorem, and I think it's gonna, no, okay. So yeah, our next theorem is that if we have a monotone sequence and it has a convergent subsequence, then the original sequence converges and has the same limit as the subsequence. Okay, so this, let's go ahead and prove this. And as usual, we'll only do one case. So we'll do the increasing case, monotone increasing case. So let's go ahead and do this. So suppose a sub n is monotone increasing, and we're also going to suppose that it has a convergent subsequence, and so we want to show that a sub n converges to the same limit as the subsequence. Okay, so remember we had a theorem in, I think it was last week's lecture at the very end, where it said that if you're convergent, this implies bounded, but not the other way around. So since our subsequence is convergent, it is bounded. Okay, and also since a sub nk is a subsequence of a sub n, and a sub n is increasing, this means that our subsequence is increasing as well, right? We're just picking out terms for our subsequence. Okay, so what do we have here? We have that our subsequence is bounded and that it's monotone increasing, and so we can say by the monotone convergence theorem that it converges to the supremum of the set of terms in our subsequence. So let's go ahead and write that down. Okay, so this is bounded and increasing. So by MCT, we know that our subsequence converges to the supremum of the terms in our subsequence. Okay, and what else do we know? We know that since a sub n is monotone increasing, that there is some actually, let's write it like this, that for some n, there is an nk, so a member of our subsequence, for which a sub n is less than or equal to a sub nk. So if we wanted to illustrate this, maybe as scratch work, we could have the sequence a sub n equals 1 minus 1 over n. This is a monotone increasing sequence. And we have a sub 1 equals 0, a sub 2 equals a half, etc. A sub 3 equals 2/3, etc., etc. And so for any term, this is just saying for any term in our original sequence, because this guy is increasing and because, we have an infinite sequence, a sub n, the subsequence is also infinite, a sub nk, we can always find something in our subsequence that is larger than something in our original sequence. So like if you chose n equals 2, if we looked at this guy in our original sequence, this is saying that we can find something in our subsequence that's bigger than 1/2. Okay, so we can find something further along here that's bigger than 1/2. So that's all that's saying. So let's continue here. And so therefore we have the following. We have a sub n is less than or equal to a sub nk. And remember, we have this guy, we're claiming that it converges the supremum of the set of terms in our subsequence. So this is always going to be less than or equal to the supremum of the set, right? That's just what the supremum means. It's going to be less than or equal to this guy. And so what we have is that a sub n is bounded above by the supremum. Okay, and so now, since we assume that a sub n was monotone, and we just deduce that a sub n is bounded above, our sequence is bounded above, by the monotone convergence theorem, we can say that it converges. So by the monotone convergence theorem, this means that a sub n converges. And by theorem 3.7, we know that if it converges to a limit, then this means that every subsequence also converges to that limit. And so L is going to be the supremum of a sub nk, which that is in n, because our our subsequence converge to that L, and so the original sequence also has to converge to that same L. Okay? So that's the proof of that guy. Here's a lemma that we're going to use to prove our final big theorem here. And you can see the proof in the textbook, but it's really, I mean, it's not a terribly complicated idea, but it's kind of annoying to write it out, I guess. But here's the lemma. Every sequence has a monotone subsequence. So even if you have some crazy sequence that looks like this, I don't even know, something that looks like this, what this is saying is that you can always pick out a monotone increasing sequence or a monotone decreasing sequence by kind of like looking at the peaks and valleys. So just from this stupid picture right here, I can pick out a monotone increasing sequence. I can say, oh, well, this is going from here to here, and then, yeah, and then we're going to have some other things over here, right? And so we can just kind of like map the peaks to the peaks so that it's constantly increasing. And you can do the same thing with the valleys. But anyway, if you want like a comprehensive proof of this, you can look at the textbook. But we're going to just use this and take it for granted here. So every sequence has a monotone subsequence. And so this is our last big theorem that we're going to need. Okay, and it's called the Bolzano-Weierstrass theorem. And it says that every bounded sequence has a convergent subsequence. So let's go ahead and prove this using our lemma. So we're going to suppose that we have a sequence that's bounded. Okay, and so we're going to use our previous lemma that every single sequence has a monotone subsequence. Has a monotone subsequence. Let's call it A sub nk. Since the original sequence is bounded, so is the subsequence. Right? Because the subsequence, we're just picking terms from the original sequence. Okay? So now we have that the subsequence is bounded, and we have that it's monotone, and so it converges by the monotone convergence theorem. Okay, so that is the proof of Theorem 3.9. So last thing I want to do is just kind of go through these, sort of a summary of what we've talked about. So decide whether the following propositions are true or false. So let's look at part A. If every proper subsequence of a sequence converges, then that original sequence converges as well. And that's going to be true by Theorem 3.7. Okay. Next one says, if your sequence contains a divergent subsequence, then the original sequence diverges. So this is going to be true as well, and it's going to be true by the contrapositive. By the contrapositive, which is logically equivalent to the original theorem of Theorem 3.7. Okay, so if it contains a divergent subsequence, then the original sequence has to diverge as well. Okay, and the final one we have here, if your sequence is monotone and contains a convergent subsequence, then it converges, and this is also true by Theorem 3.8. Okay, and I think that is all I have for you guys this week. So hopefully you enjoyed the lecture, and I'll see you guys next time. Thanks for watching.